Like I just mentioned, my class was not the only one that was impacted by this to-do list thing. So if that happened in your other classes, just reach out to the professor, and they may or may not be aware of it depending on your class size and things like that. What's weird is it affected you all, but my lecture class it didn't seem to affect. And I'm purely basing that on like everyone in my lecture class did all the quizzes, and here I had like 20% of people miss them, which I get it. If you're looking for the to-do list thing, if you're used to something and it's not there, it totally makes sense, which is why I extended it. So, anywho, there's that. All right, joke of the day. What do you got, Sophia?
What do a tick and the Eiffel Tower have in common? They're both parasites.
And I sent an announcement yesterday. I apologize, I didn't communicate this well. The week following an exam, I use for makeup exams because there's always cases. Life is far more than what happens in this room. And so at any point, if anything impacts you all that's outside of your control, let me know if it affects this course. And so in the case of exams, things happen, sicknesses, family emergencies. So I have some makeups I offer the following week based upon that. If that happens, you just provide documentation, easy peasy, we schedule it. But anywho, that's just kind of a thing that happens. So the result is I don't have like official office hours this week, but those will start again Monday. And starting this coming Monday is also when you can come by if you want to see your exam and see which questions you missed and everything. The way that'll work is I'll basically show you your Scantron. You'll like take a picture of it so you have all the things you got wrong and right. I'll show you the graded Scantron, and then I'll literally just hand you the test with like all the right answers on it, and then you can kind of go through and figure out which ones you missed and whatnot and all that jazz. But then I'll keep the exam. The exam just don't leave my room yet because I haven't tested. There is a chance I'll be able to show you all the questions with all the answers, and that is heavily dependent upon how good ChatGPT is. If ChatGPT can take my test and make a bunch of different versions that look quite different, then my workload in the hours making new exams, and so I can share old exams. If not, then every semester making a new exam takes like an insane amount of time, 20, 30 hours and stuff like that. So I tend to avoid that as well because every time I make a new exam, anytime you do something new is a chance to make a typo. And one of the worst things I can have on an exam is a typo because typos like throw people off. And I never want a typo to affect your actual performance and things like that. So that's another reason I tend to not share them. It's really hard to make a perfect test. And I was really pleased. There really wasn't a typo. I think there was one tiny little typo that someone spotted. Oh, yeah, there's the one where it's add 3 vectors. And I said add the 2 vectors to the right, and it showed 3 vectors. It said A plus B plus C. It's whatever. No one probably even noticed. But one person in both my classes noticed it. There's always something tiny like that. All right. For responses, still in progress. If you want to know more details about those, harass Peter. Lovingly. But, again, I gave him 2 weeks. So he's got to, we're in the window, and he's diligently working on all that stuff. To be fair, I'm grading a third of them. Haven't even looked at them yet either. So I'm going to plan on doing those tomorrow personally. It's just how things gone. Though I've started making the fluids PowerPoints, which I'm excited. There's so much cool stuff I'll get to teach you all with fluids and medical-ish stuff. I don't know. Fluids is really cool. I am excited I get to cover that with you all in a couple of weeks, and I'm almost done making the PowerPoints for all that good stuff. So anyway. All right. Last class. Recap. This is the most important slide. It's so important it shows up 4 times, 5 times. I don't remember the exact number. This is how we solve all energy problems. Add up all your energies you start with, and there's 3 types of energies we're going to cover in this class. Kinetic, potential due to gravity, potential due to spring. That's the only 3 in this class. There is way more types of energy than that. There's magnetic energy. There's electrical energy. There is thermal energy. There is sound energy. There is basically anything in the world that you can think about. There's so many different types. nuclear energy, like chemical energy. My goodness, the list goes on. We're only going to worry about mechanical energy in this class, which is kinetic, potential due to gravity, potential due to springs. So you'll add all those up in the beginning, however much it has. Add up all its potentials and kinetics. Then you determine, did it gain any energy or lose any energy due to friction or applied force or basically anything that's not kinetic, potential due to gravity or potential due to spring. Anything that's not gravity, springs, or motion gets chucked into here. And then you add up all your energies at the end, and all that should equal each other, and you can do stuff with it, and it's a great time. The common question, and I've gotten this a couple times, and it's a great question. When do I use this? When do I use conservation of energy versus when do I use a kinematics? And the answer is you could probably use either or for most problems. The reality is most problems you can do energy for, you can also do kinematics for. There is some exceptions. Like if I say, what's the energy lost due to friction? Obviously, you have to do energy because I used the word energy. And I said energy lost. And there is some scenarios where in general, energy is better if you don't care about the components. If you don't care about the X and Y components of things, energy is great. It's so much easier to work with. It's so powerful. We're going to do some problems eventually that if you try to do them with kinematics, it would take you much longer. And when we do them with energy, it's so much quicker. So kinematics works kind of for everything, most things. Energy is just almost like a shortcut to solve some problems. Is the benefit of it. And it does let us solve some that would just be very unpleasant. One example of this. One example of a problem that you really couldn't do with kinematics is a block goes down a hill. Here's the hill. How fast is it going at the bottom? That problem is almost impossible to do with kinematics because that hill changes the slope, and as the slope changes, the acceleration changes. And yeah, it's you just can't. Not with the skills that we have kind of in this class. So this is an example. If you have like a bumpy hill, you can't do it with kinematics, but it's such an easy problem with energy, which is cool. So we'll see examples of those, and I'll mention them. But in general, you can do an energy problem if you have a beginning and an end. That sounds kind of stupid, but in the beginning, if you know where you're located and how fast you're going, and at the end, you kind of know where you're going and how fast you're going, or you're missing one of those, then you can do energy. And it's great. It's so good. All right, great. So we talked about this, there it is, woo. We talked about the equation for work. Work is force times distance times cosine of theta, absolute value and all that good stuff. We then talked about kinetic energy, 1/2 mv squared, and this was like the OG energy. This is the first one that was quote unquote discovered. Remember, energy is not like, is it real? I don't know. But it's a weird thing that when you calculate it and then stuff happens, you calculate at the end, it's the same. So that's kind of where we left it. And now here's the next one that so we talked about kinetic. You can maybe guess what's going to come after this. I don't know. What is the work done by gravity if I lift something straight up with some initial height, y naught, to some final height, y final? So this question's both a review of work and a segue into the next thing I'm going to cover. There's only one right answer. Be careful with the negative signs and all that good stuff. And it is very important, I'll give you a hint, it's very important this is going up versus down.
I don't think it's safe because, yeah, you wouldn't do anything. Yeah,
Where does that show? Where does that show? Yeah. Nice. Yeah. Great. I don't know the song.
Yeah. I don't. Yeah.
And I learned that in middle school. Yeah. I think I got a little. Yeah. Friday. Oh, what y'all get? All right, good. What do y'all think? Why? Is anyone agree? Why? All those questions. So what was the reason for the said? So what equation? That's always equation is going to be the equation to express the correct one. So for finding words, what's the equation for word? Absolute value. Absolute value flex. That's one of them. Absolute value displacement. Absolute value of force. And then cosine theta. So absolute value force is force. Great. And absolute value is great. What's the displacement?
Yeah. So my roommate.
We're talking about gravity. Yeah, unfortunately, gravity. So gravity. So it's 180. So it's 180 All right, hint to you all, if you haven't, if you're not using the equation is the check for the logic. If your logic doesn't match the equation, then something's wrong. They should all line up. All right, so I'll give you all 5 more seconds. Absolute value of force causing the work. Absolute value of the displacement the object experiences times cosine of the angle. All right, in 3, 2, 1. Pachow. Whatever, we're just, there you go, stop. All right, great. Whatever is doing the work, that's the one we care about, the force. And we're going to draw some air. So, yeah, great. We're going to plug in the force of gravity. Fantastic. I like to draw the picture as well at this point, so I don't forget to do it later. Which way is gravity? The force of gravity? Great. Which way am I moving? Up. We're going to reference that in just a second. That's important when you're deciding this work thing. So the force due to gravity is just m times g. It's absolute value, so it's all positive. Delta x is just going to be how far you go. Final minus initial. Final minus initial. And then really the big question comes down to the cosine of the angle. If they're opposite directions, what's the angle between them? 180. Cosine of 180 is going to be -1. Again, the takeaway here, how do we understand this? Gravity slows things. On the way up, gravity is going to slow it down, which is going to decrease the energy. So the final height will be higher than the initial height. So everything will be positive, but it ends up being negative work because gravity slows it down. Yay. So we're going to use this. So how do I want to express? Well, we'll see in a second. So we're going to use this fact in a second. If we connect all the pieces, negative mg times yf minus y naught. The answer's there. All right, next question is, how high up are you right now? Are you 0 meters high, 3 meters high, 6.31 times 10 to the 6 meters high, or negative 10 meters high?
Relative to what?
What a great question. It is unspecified.
And what's me? Are we kind of
Well, what counts as me? Is it like my head?
Up to you. You decide. If it's not specified,
If it's my feet, then it's 0.
what good questions.
Like if we're going from sea level. Yeah.
I have no.
I'm definitely not doing that.
My head shirt.
Wait.
I'm not 6 meters either. So.
Yeah. That's what happened. Wait. Watch
It's negative 10.
Maybe I'll buy them all, but it will. Yeah. Just locked out on like the busy meetings. Yeah.
I didn't quite realize that.
one of those that like I didn't specify.
I didn't realize it was this so much. I worked on Monday, 7:30.
Nice. Yeah, I've seen that one before. No, it's a good one. I was
Right
like,
now, I'm more consistent, and then like the longer
all right, what'd y'all
That's
say?
exactly how I was. Yeah.
I just said relative I'm assuming C.
But it's like a 9 to 5.
That's
Makes
right.
sense. I would.
Which I think, yeah, no, you won't. All right, 5 more seconds. Go with your heart. Go with what you want to be right. All right, and 5, 4, 3, 2, 1. So I didn't plant the questions at the beginning, but the questions that the students asked at the beginning are the exact questions you basically ask yourself. Where am I measuring from and what am I measuring to? I didn't specify, so every single answer is right. It's all relative. Just like when we started at the beginning of the class, which was so good to see that people were thinking about that. Where is my origin? Where is my 0? And then what am I measuring to? Is it to the middle of my body, the top of my head, the feet? The answers I picked here, 0 meters is if you said how high I was from my feet to the floor. I make the floor 0. And what's the distance from the floor to my feet? It's 0, so that works. 3 meters doesn't quite work. We're on the 3rd floor, kind of the 2nd floor in some ways. The 1st floor kind of goes into the ground. A story and a building is like 10 feet tall. So maybe it's like 3 to 5 meters or something. So if instead you said the ground outside was your zero, we're about 3 to 5 meters above ground. From the ground, literally like the dirt outside, straight up to your feet is about 3 to 5 meters. 6.371 times 10 to the 6. It's not a random number. It does represent a distance from somewhere to somewhere. It's from your feet to a certain spot. It's the center of the earth. That's also valid. If you decide the center of the earth is your zero, then great. And the negative 10, what if instead you just said zero is like above us? Then that means I'm below it. Negative 10 means I'm below that point. And that's also fine. Long story short, every single answer is correct. And this is a useful skill. So this is going to segue us into gravitational potential energy. You all literally just derived gravitational potential energy. It's literally M times G times Y, where you're located. Now you get to decide though where this Y position, it's relative. We usually define the ground as zero, but you can pick anywhere as zero. Pro tip and a problem, either make the beginning height zero or the end height zero in your problem. That way you don't have to do math. Makes your life a little easier. If you make one of the values zero, one of these turns to zero, and it's a little bit less work. But yeah, this is something you might have seen before. It's often labeled as MGH, and I've made the executive decision I don't like it. So I changed it to Y, because I think Y is much better. H denotes a difference, whereas Y denotes a location. And that's ultimately what you're going to use. So MGY, mass times G. It's positive G. It's always going to be that positive because it's that absolute value you all saw when you derived it 2 problems ago. This is just due to the work due to gravity. We are not going to calculate the work due to gravity moving forward. If you want the work due to gravity, just subtract 2 potential energies and you have it. Technically the negative. If you all remember, Yeah, you all effectively, you derived it before. The work due to gravity is just the negative change in potential energy due to gravity. You all found the work before. If you just put in the things and you compare the two, it's just the negative change in it. So yeah, we're not going to calculate work due to gravity, long story short, moving forward. We did it a couple times to practice work, but moving forward, if you want to find the energy of lifting something, you just do MGY. And this is where I'll now ask a question that I don't think I have here. All right, I already asked this question before with kinetic energy, so I'm going to ask it again with potential. Can potential energy due to gravity be negative? Yes. Yay. No. Who can say? Whatever.
If it's not the one like right before it was like the percent of what you use, so it's going down to 99.
And this isn't the change, this is just the term itself, MGY. Can that be negative?
Actually, no.
So, say like something like in space, no gravitational pull around it. Would be
If you're drawing.
Yeah, so we're not going to go, unfortunately, I kind of mixed this equation. So there's an equation for the force. We've been using the force of gravity mg. That only works when you're on Earth's surface. When you get away from Earth's surface, g is not 9.8. It's literally everywhere. So there's a fancier equation that's over r squared.
Oh, yeah, the inverse square.
Yeah, it's g m1 m2 over r squared. Well, you can then use that to get the potential energy equation. And g m1 m2 over r. So long story short, it's over r. When does that turn to 0?
No, UG is what the time is.
You're like, I'll never get. Might as well, but you can't see that. You get far enough away from the Earth, up to Pluto, Jupiter, even. Sure, the Earth's got you, but it's so small. Basically zero.
If you're dropping it, your initial zero.
So yeah, infinitely far away. The gravitational structure is zero.
Yeah.
All right, 5 more seconds.
You're gaining energy.
In 5, 4, 3, 1. All right, to answer this question, we're going to go through each terms. Can the mass be negative? No. No negative mass that we are aware of in physics. That we are aware of. You know, who knows? If you ever prove me wrong, you won the Nobel Prize. That'll be your reward for proving me wrong. And then going back to this problem, remember we took the absolute value of force. That meant we took the absolute value of G. So G is also positive here. So mass is always positive. Gravity is always positive. And then the Y position, to answer this one, I'm going to go back to this. Negative is a viable answer. Negative position is a viable possibility. It's all about where you define zero is. Zero at. If you're below ground, then you have zero potential energy. If you go below ground, you get negative potential energy. That means you have less. And it's a scalar in this case. So long story short, Y can be plus or minus. So yeah, can it be negative? Yeah. And all I want to point out here is that 10 joules is bigger than 0 joules is bigger than negative 10 joules. Negative energy doesn't mean direction. It means a smaller number. Just like if we have negative work, that means you lost energy. Negative in scalars does mean smaller. Whereas vectors, it means direction. It's one of those things you just got to be careful of. So, fun fact, this is the only energy we're going to talk about that can be, out of the 3 I'm going to teach you, kinetic, potential energy due to gravity, and potential energy due to a spring. This is the only one that can be negative. We'll see when we get to the next equation. That one can't be negative. Work can be negative, but this is the only one that can be negative. All right. Great. This should be... What is the gravitational potential energy for a 10 kilogram object that is 5 meters? I'm going to change it to make it more interesting. Below the ground. And then I'm going to change every single answer here. So you have no idea which one's right. 490 joules, negative 490 joules, 50 joules, negative 50 joules. Great. How do we do on the last one? Oh, great. We're okay with the negative. Yay. I thought it'd be worse. And here I tell you where 0 is. I define 0 here. In almost every problem I give you, I won't define 0, which is good for you. You get to define it, which is nice. But this one I do define it. Otherwise, every answer would be right.
Because the 5 is the final. I said that the 5 is the final, the Y final.
So
Because it's above the ground, and the ground is 0.
We're not looking at the change. We're just looking at what is the potential energy at that spot.
and also
Yeah, but like,
Oh, 5 below the ground. Oh my god. I missed that.
And our zero.
-90.
Yay, what's our unit for energy? Without looking
Oh, because on this that I'm reading.
Everything's
Okay.
It's all the same person.
I was reading this.
so what do you need?
So you wouldn't normally have to do
What'd y'all get over here?
the Wi-Fi.
Okay. Yeah, something else. It doesn't actually matter how much energy you have. It matters how much your energy changes.
You'll rent
It's the easy way to do it. That's why, like, you can define zeros anywhere. So I could say, if I didn't define zero, if I made it so it would have like a crazy amount of energy. Which doesn't matter. All that matters is how much your energy changes. That's how I'm solving it. It's always a change.
Okay, so this is our next one.
All right. We'll go like 15 more seconds. Yeah.
Why is the always to be?
Because this got derived from work. Remember, work was the absolute value of force.
Oh, okay.
So it kind of came from that. Yeah. That's a good question.
So potential energy, you get energy that can be converted
It can be converted to lots of. Yeah, it often is converted. But it can be converted to many things.
all positive. So what is that?
Yeah, so the next thing I'm going to let you on, it doesn't matter how much energy you have, it matters how much energy changes. It's all about change. And I'll give you all a couple examples of this in a second. All right, in 5, 4, 3, 2, 1. Ka-chow. All right, so if I did not tell you what 0 was, if I did not tell you the ground was 0, every single one of these answers would be viable, which is but I did tell you the ground is 0, so they're not all viable. The reason I mention this, it doesn't matter how much energy you have. It doesn't matter how much energy you have. It matters how much your energy changes. It's all about a change in energy, and anytime we work with energy, that's the case. So another example of this is, how fast are you moving right now?
So what?
Exactly, relative to what? I could say your velocity is 0 relative to this room. Your velocity relative to the sun, you're attached to the earth, and the earth is slingshotting its way around the sun and going extremely fast. I could say you all have like an insane amount of kinetic energy right now, because you're technically moving relative to the sun. What does that mean? Absolutely nothing unless the earth came to a complete stop. It means nothing unless the earth like ran into something and came to a stop and your energy went from a lot to nothing. So whenever what changes, it's not about the actual individual quantities of energy. That's why the relative doesn't matter. Anywho, in this case though, I did give you all a reference. Oh, and I'm also going to note this now. You might see me do this because I don't really have a preference. You might see me put potential energy as PEG, or you might see me put it as UG. They mean the exact thing. Some people prefer to put PE because it's a nice shorthand for potential energy and it's easier to remember. For whatever reason, physicists at some point decided to use U. I think they just wanted one letter. I don't know why they chose U, but they did. Here we are. Maybe Peter knows. Peter, do you have any idea? No, neither. See, we're in Ask ChatGPT. So great, it's MGY. You plug in the numbers. Remember, when we plug in G, it's going to be positive 9.8. That came from the whole absolute value of work and all that good stuff. Our Y here is negative 5, because if we look at our picture, we're going to define Y equals 0 as the ground, and if I'm 5 meters below that, then I'm at Y equals negative 5. And, 490 joules, yay. Again, the amount doesn't matter, this is just practicing plugging numbers into this equation, but the reality is in physics, when you actually do a whole energy problem, it's all about the change. It's all about change. Yeah. That is a great point that if you look at this later will very much confuse you. Thank you. There you go. I would have realized that if I actually plugged it in the calculator, but I didn't. I just was like, oh, that's the answer. Yeah.
Why is 9.8 not negative?
Yeah, why is 9.8 not negative? It's a great question. So remember, this equation didn't come out of thin air. This MGY, this came from the work equation. And when we did the work equation, it was absolute value of the force of gravity. And so that turned it into a positive. It's a great question. It comes from the derivation, basically. So moving forward, just remember G is not positive 9.8 when you all do this. Why is that? It comes from where it was derived from.
I'd like to add something. If you did have G as a negative number here, the potential energy would go up as the object fell further down. And if you think about it, that doesn't make any sense, right?
Yeah, so say we start at 0. Say we start at 0. How much energy would I have? How much potential, if we start at 0, how much gravitational potential energy do you all have? 0. Right now, if we go downwards, we're ending up with a lower negative potential energy. And this one we have to do kind of conservation of energy to actually like...
Yeah, so if something falls, potential energy goes down, kinetic energy goes up. If the potential energy was also going up, then you'd be breaking conservation of energy.
Yeah, so we're going to see very soon, we're going to derive conservation of energy. We're going to derive that equation that I've been showing you on 4 different slides. And we need potential energy to go down. And again, honestly, the answer is it comes from this. Like that's the most straightforward answer. The one is it comes from the work equation. But I'm going to show you all that it then also works out with conservation of energy. And if you add it backwards, things don't work out the way you want them to. So I already mentioned this on this slide here somewhere. There it is. If you just go through the motions, you find that work is the negative change in potential energy. And you can see it kind of written here. You all derived work on one slide. And then I just swapped it with delta y. And then if I compare this to this, it's the negative change in that. Feel free to check that out at some point and make sense of that. But if it doesn't make sense for now, just trust me. Sometimes that's how things end up. So work is the negative change in potential. But work is also the positive change in kinetic. And again, that derivation I can't quite show you all because it involves calculus. So for now, just trust me. It's a positive change in kinetic. So if you all write this out, you have the negative potential energy final minus potential energy initial. Change is just final minus initial, and I have a negative sign in front of it. Here I have kinetic energy final minus kinetic energy initial. This is not something... Work equals work, right? Like that's not a crazy idea. So then we're just going to plug this in. So the negative potential energy change, and I'm going to go ahead and transfer that negative just so I don't have to do it later, equals the kinetic energy final minus kinetic energy initial. Literally all I did was swap them in. I put this work here. I'm not doing any crazy steps here. I put this work here. They both equal work. Work. Great. So what? Rearrange it. Put all the finals on the same side. So if I want to move the potential energy final to the other side, I add it over. How much room do I have? A lot if I move this picture. Just move all the finals to one side and all the initials to one side. And you have the energy you start with equals the energy you end with. Yay! It's conservation of energy. The energy I start with equals the energy I end with. Again, you don't need to know, like, it's just nice to see that. Now, what this is neglecting if I push something or if there's friction. And so that's where, remember, the magic equation that we're actually going to use is add up all the energies plus work equals energy final. So this work here is everything we didn't account for. We only accounted for kinetic and potential here. We only accounted for motion and gravity. What about if there's friction? What about if there's someone pushing it? What if? That gets chucked in here in this extra term. So. Yeah, this is an equation you all might have seen in middle school or elementary school or, I don't know, high school. If you didn't, that's fine. You see it now. The energy I start with is the energy I end with. But that's where it comes from. Kind of, sort of. It's all a circular logic at the end of the day. which is yeah, it all came from kinetic energy first, but great. And now we practice. Ka-chow. All right. How long? Nope, can't do this one. No, we can. Do I want to do this one now or later? We're gonna do it now. It's not that bad. It seems worse than it is. You just gotta. I forgot to remind you all. We also learned about power, and we looked at my electrical bill. So I'll kind of remind you all of that as we solve this one. So how long will it take an 850 kilogram car with a useful power output of 40 horsepower, 1 horsepower equals 746 watts, to reach a speed of 15 meters per second, neglecting friction? How long will this acceleration take if the car also climbs a 3-meter high hill in the process? So a key phrase here is useful power output. We don't have to worry about the efficiency of the motor or anything like that. We just say this is how much energy it spits out every second. However it does it, whether it does it with electric motor or gas motor, who cares? It is able to do, every second, it is able to output 746 joules. Remember, watts is how many joules per second. So every second, I can increase my energy by 746 is what that term means. Great. Go ahead and write your givens. Try that step out. You could draw a picture if you want to. It won't hurt. But yeah, this one I'll walk you all through a little bit. Oh, but pro tip, every single time you'll have an energy problem, just assume you're going to start with this equation. Energy initial plus work equals energy final. Like, I'm just going to chuck that there now because we're going to use it. Yeah, and don't feel like you need to wait on me. We have this one. I'll also straight up tell you, if you all see the word power in a problem, there is literally only one equation with power in it. Like, it's not even a choice of what equation do I use with power. There is literally only one equation with power in it. So see if you all can remember what that equation was, look through stuff, whatever. It's good to help remember that before I give it to y'all. It's in the formula sheet. It's literally the only variable. Okay, this is going to be very unfortunate. I'm going to warn you all, power is going to be P. When we learn about fluids, pressure is also going to be P. It's very sad for us. I didn't make the rules.
Most physicists probably wish there were more letters.
Hence why we go to the Greek alphabet. But someone at some
We
point...
start running out of those too.
Yeah, that's true.
I'm not sure I can even count how many different things mu is.
Yeah, that's true. Yeah, at some point variables get reused and you just have to know the context you're in.
Latin.
If only.
This is Latin. Use the same alphabet.
Wait, no. What is the one where like sigma is like the weird like O thing? With, like,
Greek, that's also Greek.
Capital
well, I
and
thought
lowercase
sigma was the
There's capital and lowercase. Yeah, we use both. So we have 26 letters in the English alphabet, uppercase and lowercase. I don't know how many are in the Greek alphabet.
I think it's about the same.
Maybe about the same, uppercase and lowercase, still not enough. All right, if y'all haven't found the equation, power equals work over time. It's a really easy equation. All right, the speed. Anytime you on 15 meters per second, great. It's velocity. You always have to make a judgment call, beginning or end. This is going to be the final velocity. It says to reach this speed. So this is a final velocity. And if ever we talk about a final, that means you should probably also be thinking about, I wonder what the initial is. I'm not going to tell you. I'm going to let you figure that out. And then we are solving for how long will it take? If anyone ever asks you how long something takes, what are you measuring? Time, always.
Question.
Yeah.
Power output is 40 horsepower. 746 is the conversion factor.
Correct. Great catch. I assume this was a weak motor with 1 horsepower. That's lousy. Yeah, I made the mistake of I just like, oh, look, a number. And then I just put the number down, and that was silly of me. If you put this as your power, it's wrong. This is actually not much power. A 1 horsepower motor is not going to get your car anywhere. So be careful of this. Don't just write down the number you see in a problem. Think about whether it's actually the number it should be. All right, I have no idea what this number is.
It's
29,840 watts. Great. I've actually done all the I've almost done all the physics for you. The equation is there. You all need to build that equation. Every single energy problem, you all need to build the equation. What energies do I start with? What energies do I end with? Is there anything adding energy? That's the work term. Try to fill in the gaps. Try it for yourself. See if you can do it. What energy? I've only taught you all 2 types of energy so far. Kinetic and gravitational. What do I start with? What do I end with in those categories? Yeah, we're going to assume so. Yeah, if not specified otherwise. Because if it was already traveling that fast, then 0 seconds. Yeah, and this is one of those, if I give a test from, don't specify that.
The thing is,
This is good. This is fun. It is fun. Look, this one is so close. There's just a couple gaps y'all gotta fill in.
We're not at the 3 meters yet.
Oh, the nice thing is the 3 meters is like if you do part A, part B is adding a little bit.
Use 3 meters.
If only. If only. You could do that if gravitation, if it wasn't moving as well. But because it's moving, you have, in part A, you have only 1 type of energy. It's from 2. Your goal is to build that energy equation. What energy do I start with? What energy do I end with?
Would you use gravity for the first part, or is that
It's a great question. So think about what's the equation for potential energy due to gravity? And UI. Go ahead. Where do you want 0 to be in this problem? Where does my start part? Where does my car start?
the ground? So
Where does it end at? It doesn't change. Yeah, at the end of the day, you could say the car started at 100, but if it also ends at 100,
So you're going to use that for part B.
because its height actually changes.
Okay.
Yeah. You only care about the energies that actually change.
Correct.
Did you all figure out what energy it starts with? Hey, let's do what it is. What is it? What type of energy? Yeah, there's only 2 choices. So at the end, doesn't have to be
But if it equals also 1,
What's the equation?
is it equals energy final? So if there's no work on it, it would work with the zero.
What do you all want y to be 0?
Then if we have the
Great, is that the ground? Okay, at the end, is that the ground? Above the ground is the lower. Right? We find the ground 0. The ground. Great. So the end is let's go to the beginning. Let's just look at potential. Above ground, below ground. At the ground. 0. Great. We're gonna sit there. Great. That's all my energy. My energy down to 0. My energy final. So I went from 0 to something. How did that happen?
So now maybe you can
work is equal
That don't have any
have power.
Alright, so there's literally only 2 types of energy we start with. Or 2 types of energy we talked about. So we just go through the checklist. What are the 2 types of energy? Kinetic and potential. So you ask yourself, first, which one do y'all want to look at first? Kinetic or potential? I don't care. Kinetic it is. Kinetic, am I moving at the beginning? No. Velocity initial is 0. So one of the things you can honestly do with this, it's going to look really jank, and but it's a good potential energy initial plus work. You can write this whole thing out. I say jank. It's just extra writing. It's not bad. What I am writing is the exact same thing, but great. The energy I start with, kinetic plus potential plus work equals the kinetic energy, or the energy I am with. My kinetic energy in the beginning is 0 because my velocity is 0. Kinetic energy is 1/2 mv squared. If v is 0, this is 0. Great. Okay, potential energy, mg, not h. I'm in the bad, I think y is better. We have to make a judgment call, mgy. Where do you all want 0 to be? You get to decide. Where would we like to place y equals 0? The ground. Where does my car start? The ground. So if y'all draw a picture of this, here's my car. Here's my car. Y equals 0. So my potential energy in the beginning is also 0. It has no potential energy to begin with. Great. So I'm going to start writing this in step 4, 0. We're going to worry about work in a second. Let's just stick with energy. Kinetic energy final. Am I moving at the end?
Yes.
Yeah, I'm moving at the end. So I have some kinetic energy. 1/2 times mass velocity final squared. Great. Plus, where am I located at the end? Above ground, below ground, or at ground? At ground. What's my potential energy at the end? Don't know why I put a 0 there. It's 0. Great. So the left side says 0 plus something equals 1/2 mv squared. How do I increase my energy? What's the word that says how much my energy increased or decreased? Power. Or, not quite power, but close. Work is going to be, but we're going to use power. Work is how much energy you increased or decreased. Now, here's the problem with work. Do we know normally we would say, oh, force, distance, cosine theta. Do you all know the force? Now, do you all know the distance? No, we can't use that. If only we had another equation with work in it. We have the power equation. If you just rearrange it, work equals power times time. Yay, we did it. We built the equation. Every single energy problem is just building the equation. What energy do I start with? What energy do I end with? Is work being done? And you build. After you all do, this is like force problems in that you have to build, like the force problems, you had to build the equations, F equals ma. This one, you got to build the energy equation. Once you do a few of these, it's very straightforward. Plug stuff in, try out the final steps.
And then
Totally.
there, okay.
It's the exact same process.
It's just faster to do it this way.
It's all in one go as opposed to splitting it up.
Okay.
Yeah, you could totally find the work done and then plugging it.
Okay.
For some people, that might be easier to see.
Okay.
I do.
I found the first one from
Yeah, someone had a good point. If you're like, whoa, what happened here? You could solve for the work, and then you could plug it into the power equation. You're doing the same thing, but that might be easier to see. You could solve for the work and then plug that into the power equation if you wanted to. It ends up being the same work either way, but that might be easier to see.
Watts per horsepower.
Oh yeah, if you get part A, do part B. It's the same same thought process. What energy do I start with? What energy do I end with? Is there work being done? You do that and it all works out.
I will say you don't. Just use the I think it all because it can also
So yeah, try to build part B. Try to build the equation. Try to build.
No, it's you know what?
Really?
Yeah, I saw it for work. And then I flushed. Then you already had it. I did this equation.
Yeah, B is asking for the same thing, but the situation changed. So part B, it says, great, I want to go from 0 to 3. I also want to go 3 meters higher. And how long is it? That's all. That's all you need. That is the amount. It's like F equals MA, but for energy. So what energy do you start with? What energy do you end with? What's doing the work? All right. How's part B go? Nice. Honestly, if you can do part B every single day, it's hard. The only thing that might vary is maybe instead of working the power equation, maybe we'll actually the work equation. Like, so maybe I would, yeah. So maybe I'll give you the beginning and the end, like I did in this problem for energy, and I'll say find the force due to friction. And you'll just replace work with F times delta X. Yeah, there's one more additional energy term, which is for spring. I'll teach you all. So if there's a spring underneath that, it'll just be the whole that we think about, and that's it. But the process is literally this for every single time. It's great. It's so straightforward. It's so like that's why I think it's once you do one or two of these, you do all. Alright, let's go with the big one. What's different about
That's the work done by we're looking for.
Alright, so for part B, if you haven't done it yet, literally the only difference, and this is where pictures can help you. In part B, your car starts at the ground still, but then it goes up a hill. What's really cool is we don't care what the hill looks like. We don't care if it's a bumpy hill. We don't care if they like went up and then down. You do not care how it got there. You just care that it's there. Because of no friction. If there's friction, then we care. And it's unpleasant. All right. So, long story short, our thing ends up being there is no kinetic energy to begin with. There is no, like, that hasn't changed. Our initial condition is the same. So, great. We start with no energy. Then some work is done. And then what energies do we end with? In part A, we ended with kinetic. In part B, we're going to end with kinetic and potential. Because now we're above zero. It's not about being above ground per se. It's about being above your zero. We happen to define the ground as zero. You can define anything you want as zero as long as you're consistent. So we define this as zero. At the end, it's 3 meters high. It's all relative. If we wanted to, we could have defined the ground as 1,000,000 meters. And then my final would be 1,000,000 plus 3. And it all works out the same mathematically. You all could have made the ground -3 and made the final 0. And it all works out the same. It's all about the change. Do I want to mention this now? I'll mention it a little bit later after we do enough of these. If you understand potential energy with gravity, you can understand batteries. And you'll be like, what? Batteries do not work on gravity, but I'll explain that eventually. You'll see that in physics too. All right, great. I've taught you all 2 out of the 3 energies. The last energy. So we have kinetic. We have potential due to gravity, and the last one is a spring. I don't know why physicists love springs. I kind of know why, but whatever. I think it's because you can model a lot of things as a spring, which sounds silly. But like you can model the forces between molecules as a spring, which sounds really weird. You can model a crystal lattice as a bunch of atoms stuck together by springs. You can actually model the electrons' energy levels as a spring, which is weird. Quantum mechanics, it's one of the simple harmonic oscillator. I don't know. I think that's the reason. Whatever, there's the equation, 1/2 kx squared. K is the spring constant, and actually, do I want to leave it as x? I never liked this x, so I'm going to put delta x. And I'll change it on the formula sheet as well. It is often reported as just x. The reality is it's delta x. It's a distance from the equilibrium position. I'll draw a pretty picture of this. There's my spring, all happy. In fact, here's my spring, all happy. Delta x is how much a spring gets squished or stretched. It's not how big the spring is, it's how much you stretch it or you squish it. And you all did the lab on this if you remember that. You didn't measure how big the spring was, you measured how much it got stretched. K is a spring constant. K literally is saying how much force you need to compress it 1 meter or stretch it 1 meter. K is always a positive number. Always. There's no such thing as a spring that has a negative spring constant. That'd be wild. Trying to think what that would mean, that it required negative force to stretch it. Which I don't know what that would mean.
Like you're pressing it and it's stretching. Like
Yeah, it would mean that if you squished it, it's stretched. Which doesn't make sense. So yeah, a negative spring constant would mean that if you squished it, it's stretched, or if you try to squish it, or if you try to stretch it, it's squished, which is nonsense. No spring works that way. So always positive. Yeah, so I'm not going to even ask. Sure, I'll ask the question for continuity's sake. I've done it for the other two. Maybe you can guess. Can the elastic spring energy be negative? Yes. No. I hate this question.
Oh wait, no, he said all yeah, only
Per chance.
negative energy is
Great. Mark that one as right. I'll even write the equation for you all. So again, this is still a U, but we put a little S next to it, or we put potential energy spring.
oh my god, I'm
Even if it does.
so like one of
the
those
worst is when you wake up at 45
Who
and then you wake up for class and I'm still tired. Yeah. That's what happened to me. I went to bed. And I was like, oh, it'll go away when I'm asleep.
All right, 10 more seconds. In 5, 4, 3, 2, 1. Ka-chow. All right. K is always positive. Yay. Displacement, now it's defined as distance displacement. It doesn't really matter. Let's pretend like it could be positive or negative, the displacement. But who cares? It gets squared. So it turns into a positive. So no. Just like 1/2 mv squared. It's kind of the same form. Mass can't be negative. Velocity could be, but it gets squared, so who cares? So long story short, the only energy that could be negative, just literally do the equations, is potential energy due to gravity. Does that mean anything? No. It's just how the equations work. There's no grand meaning to that gravitational potential energy could be negative, in my opinion. Maybe people have different opinions on that, but it's just how the math works out. And it's just one of those, I want to remind you all of that. Because kinetic energy can only be positive and because spring energy can only be positive, people then often think that gravitational potential energy can only be positive, and that's not true. So that's really the reason I asked this, is actually to show you one of them can be negative. Just make sure you make it negative. All right. I think this is the last time it finally shows up. Wow, it's the equation again. But what I want to point out to you is now that we've learned all the pieces, we started with this equation and I've slowly been teaching you the pieces. So I'm just going to rewrite this for this class. On the formula sheet, it's going to be something like this. In fact, I'll probably make it this if I haven't done so already. But to write this out, in this class, there is literally only 3 types of energy. Kinetic. So kinetic energy initial plus gravitational energy initial plus spring energy initial. Great, that's all my starting energies, plus work, which isn't 0, could be anything, equals kinetic energy final plus potential energy final plus spring energy final. This is basically how you solve every single problem, is this long thing. Do I start with kinetic energy? It looks worse, it looks bad, but it's really easy. Am I moving in the beginning? If I'm not moving, kinetic energy goes away. Am I above 0 or below 0 at the beginning? If not, This one goes away. Is there even a spring at all? If there's not a spring, guess what? There's no spring energy. It's literally just a checklist you go through. The one thing I want to point out, and then you do the same at the end. Am I moving at the end? Am I above or below 0 at the end? Is there a spring at the end? A spring that's compressed or squished? Great, you do all that. And then you say, is there any work done? And I really want to make sure you are careful of this. When we're doing this work, it's work due to applied force or friction force. Do not do the work due to gravity. Do not do the work due to a spring. We've already accounted this. Do not say, is there work due to gravity? Because you're already doing that. You're already accounting for gravity with these terms. Do not double count for gravity. We practice problems to find the work due to gravity because it let us derive this equation. Moving forward, do not do the work due to gravity unless I specifically say find the work due to gravity.
If it helps, think of it as work coming from outside the system.
Yes. Yeah, work. Pushing it. Friction. That's basically the main two ones. There's not really... Something's pushing or pulling it outside of it. Applied force, friction, something like that. And yeah, Tuesday we're just going to go through a bunch of these. Literally, the rest of my PowerPoint slide is like, how many examples? 4? 4 different examples of doing these. So we'll do that Tuesday. But before we get to that, do I want to do this? Yeah, I do. I'm going to do this one now because I might ask a couple more of these on Monday because I want you all to... This is a interesting one. If an object is dropped from a height of 10 meters, at what height is the kinetic energy twice as large as the potential energy at that same height? And be like, what? At that height at the end. So, let's draw a picture of this. I dropped something from some height of 10 meters. Yay. And then the question is, at some mystery height, at what height, what is that value? Y final equals question mark. At what height is my kinetic energy? Oh, is this kinetic energy final or kinetic energy initial? Final. At what height is my kinetic energy final equal twice my potential energy final? At this height, that happens. Assume no air resistance. Yeah, I'm going to see if y'all... You're going to build the equation still. Still build that equation, y'all, the energy equation. And I'll even be... Yeah, build the energy initial plus work equals energy final. You have to do this one. Do not try to intuitively jump to what the answer is because it won't go well for you. You got to build it. Build it. What energy do I start with? What energy do I end with? Is any work being done?
What's the math?
If it doesn't tell us, then maybe it can't be.
This is easy. You do have to think about it.
At the beginning, 100% of your energy is potential. Where is it? Where is your potential energy?
Yeah, perfect. So we have potential energy initial equals potential energy final plus potential energy final.
Figure out when
We have a relationship between. So you can swap kinetic energy with 2 times and then see what happens. Yeah, you basically have to. And then you can the actual equation.
so you see all the white holes are the center of the universe, and that's why things
I'm wondering, at what height does this happen? At what height is my kinetic energy twice as large as my potential energy? But yeah, the key here, y'all, is build the equation. Build the equation. That's the skill that we're doing here. What energies do I start with? Do I start with gravitational potential energy, kinetic energy, spring energy? What energies do I end with? Am I ending with kinetic energy, spring energy, gravitational potential energy? For now, just start building that. Even if you're like, I don't know how this is going to be helpful. You will see. Trust the process. Trust the process. So I'll give you all like a few more moments to build that, and then I'll show you all the next step.
So we just said work extra. Gravity's already accounted for. So we have the potential energy from gravity already in the conservation method. The work done by gravity is already accounted for. You don't need to calculate this again. Your double counter gravity.
Actually, just
All right. So is my thing moving at beginning? If I hold my water bottle and not moving, great. No kinetic energy to begin with. Is there a spring in the beginning? No. Where do y'all want 0 to be?
There's no external work. The work.
Let's make the ground 0. Am I above the 0? Yeah, great. So that one exists. Great, done. Let's look at the end. Then we'll come back to do work. Am I moving at the end? Yep. Is there a spring at the end? No. Am I above ground at the end? Yeah. So let's just, and then the last thing, then we go back and work. Is there any applied force? Is there any friction? Is there any air resistance on this object? No. Work is 0. There is no other forces. Gravity is the only force acting on it. We're already accounting for gravity. So now we write this out. So gravitational potential energy initial equals kinetic energy final plus potential energy final. And then you look at this and you say, great, I know how high I started, so I could find the first term. But you say, I don't know how fast I'm going. Correct. We have another expression written somewhere. So I'm going to see if you all can figure out, there's two equations right next to each other that we're going to, there's an equation we're going to want to reference that we wrote in our picture.
So you just know you one part of this, 2 parts of this.
Remember, one of the criteria I gave you all is that the final kinetic energy is twice the potential energy final. Swap it in. Potential energy initial equals 2 times the potential energy final. And I know I used PE and I used U's here, which is a little unfortunate. U. You can swap that in and then try it.
So at the beginning,
plug in still.
Kinetic energy at the beginning plus potential energy at the beginning. What's your kinetic energy at the beginning?
So this problem,
at the end,
it's saying
kinetic
at what
energy
height
at the end plus
is the
potential energy
kinetic
at the
energy
end.
twice as large?
The end is when
Yeah, I mean that. There's a chance that could be the answer, but yeah.
That's what we're looking for. When is that? So Ke equals 2E. So if you but at the end you have some amount of kinetic energy, some amount of potential energy. You know that the kinetic energy is equal to 2 times the potential. So you can plug that in.
All right, so this is I've given you all at this point I'm going to leave the rest to you.
Some amount.
I'll show you the answer after I close it. So give it a good college try.
And then you have to calculate.
Also, you get rid of the
Plug in 2.
Yeah. So this one is it's just getting used to working in variables, honestly. And that if you have constraints, you can use those constraints. In some ways, it's kind of like the problem where you had the two people running, and it was at what time.
Oh, yeah.
It's realizing if you're solving for something at a special condition, that condition is an equation in and of itself that you can then use.
So, no.
Yeah, it's just one of those kind of like conditions. How are you doing over here, Jan? Figure it out.
I'm not sure how to actually connect this in a way that I can
Working on it.
because I just got 1/3 out of my mouth. But I'm not entirely sure how to explain it.
Set up math.
Oh, you actually to the final?
That's not the right math.
That is not correct.
But it works.
Yeah, we have kinetic energy initial plus potential energy. Kinetic energy final.
Yeah.
Yeah, that's what I mean. That's why I have yeah, so that's our constraint. So in some ways, it's almost like yeah, realizing that our criteria for the answer has an equation. Like the people running, at what time is their position the same? Their position being the same is an equation. At what height is the negative equals twice the equation? That's like a new equation.
But we don't even need it.
Yeah.
Well, we need it.
Oh, that makes sense.
All right, give y'all 5 more seconds, and then I'll close it out.
The work is only stuff from outside.
All right, in 5, 4, 3, 2, 1. All right. The challenge really to this problem is realizing that the final answer is an equation. Like, it's kind of like the two people running problem. Remember Pablo and Jacob, at what time are their final positions equal? Their final positions being equal is an equation. It says, it gives you a relationship. At what height is the kinetic energy twice as large as the potential energy? That's an equation you can write down. That's a constraint between two. It's a relationship between two variables. So if I just take this thing, and I write it over here. So potential energy initial equals 3. 2 plus 1 is 3. And then I have mgy initial equals 3 times mgy final, which works out really nice. Mass cancels, gravity cancels. And you get y initial equals 3 times y final. So 10 equals 3y final. And the answer is 3.33. The challenge to this problem is realizing the constraint that at the end, the kinetic energy is twice the potential, and just writing that. Anytime a problem says this equals this at some point, or this equals this at some point, that's an equation you should write down. An equation is just a relationship between two variables. That's all an equation is. Write it down, then you can use it in math. All right. Go ahead, take a breather. 9:35. We'll start our lab. You can start joining the groups now if you want. Up to you. Obviously, don't start the lab yet because I got to explain things, but you can start joining groups, max of 3, yada yada. Tuesday, we'll do another one of these. Tuesday, right after this, I'll do another one.
So I was like, I was like,
Yeah, it's a different type. So it's working in equations. Yeah, people often want to jump to like, oh, I built the Kinect. Immediately put in the equations for those. Sometimes it's good to like.
yeah, and I don't know. When I took physics, I don't know. I guess if I could those just never broke down like that.
Okay.
So this is like my first time seeing it. Like,
Good. One of the
but it
things.
makes sense. Like it makes sense now. But
Yeah. That's one of the cool things of being in LA and DTA is. So you did well on the course. Like that's how you ended up in LA. You're gonna find that being in LA, you do know a lot because that's what got you here. But you're gonna realize both. Wow, I really didn't understand this as well. Like
yeah.
I did well, but like there's so the conceptual understanding that takes time, and often so like that same thing happened to me when I was in LA. Voltage and current. I got through my whole undergraduate problems with them. Did not understand what they were until I became in LA my junior or senior years of physics major.
Yeah, like it. I think that's what's been interesting so far. Is like obviously like I knew the
Yeah.
equations,
But now you get
but
yeah.
I've never seen it like broken down. But now it like
And some of that just comes from you have to sometimes just know how to do it at first before you can actually understand the depth of it. Yeah, it's one of the cool things about teaching something. You get to learn it way more in depth because you have to because you have to explain things.
Right.
Yeah. Sure.
So, you said
Just join any group that has 2 people. Yeah, just hunt around. In fact, someone over there. Yeah, just hunt around. I think there's someone here that usually has someone and he's not here. So, or they normally have 2 people and you join their group.
that group of them?
Yeah. You all normally only have 2 people, right? And I guess the other person, I have a different person. Yeah, that's cool. This time. Great. His life partner's not here today.
Oh, that's true. We just have one left person.
I think I just like share.
Huh? Or what? Oh, they ignore it this time as well. I always ignore it. One day I'll maybe chuck it at the end instead of the beginning. Yeah, it's something I did last semester, which had some value, but we always run tight on time. So